c of f of x, and it's equal to L. So in terms of what an actual problem is going to look like, if we look down here at example 2, again, we're going to start with this numerical approach. So that means we're going to be creating a table. So within this table, you can see my c value is 2. So my x value is approaching, or x is approaching 2, so 2 is my c. I'm putting 2 right here in the middle, and then I'm going to pick x values that are a little bit bigger than 2 and x values that are a little bit smaller than 2. My function, what I'm evaluating the limit of, is 3x minus 2. So that's what I'm going to plug in these different x values. I'm going to plug in 1.9 in for x in my f of x. So doing that, I'm finding f of 1.9. That simplifies to 3.7. So I encourage you to make sure when you evaluate f of x at these different x values, you are getting the same thing. We'll find f of 1.99. So doing that, I end up with 3.97. Plugging in 1.999, I get 3.997. We're going to skip over. I'm not going to plug in 2. I'm going to start with x values now that are bigger than 2, so 2.1. Plugging that in, I get 4.3. Plugging in 2.01, I get 4.03, and then plugging in 2.001, I'm getting 4.003. Okay, so as we're looking at the x values from the right of 2 and to the left of 2, we can see that my y values, or my f of x values, are getting closer and closer to a particular value. So from the left, it looks like we're getting closer and closer to a y value of 4. From the right, it looks like it's getting closer and closer to 4 as well. So that leads us to believe that the limit as x approaches 2 of 3x minus 2 is in fact 4. Okay, now we're going to look at another example. Okay, same idea. We're going to use a table, and we're going to estimate numerically the value of the limit. So we're finding the limit as x approaches 0. My function this time is x over the square root of x plus 1 and then minus 1. Again, my c value is 0. So I'm putting 0 here in the middle of my table, and I'm picking x values that are getting closer and closer to 0 from the right, x values that are getting closer and closer to 0 from the left. And we're going to do the same thing. I'm going to take this x over the square root of x plus 1 minus 1. That's my f of x. That's my function. I'm going to plug in negative 0.1 for x and simplify. So doing that, I get 1.949. An x value of negative 0.01 is even closer to an x value of 0. So plugging that in, I get 1.995. This x value is even closer to 0. So plugging negative 0.001 in for x in my function, I'm getting 1.999. So as x is approaching 0 from the left, we can see that my function appears to be getting closer and closer to 2. Okay, so 1.949, 1.995, 1.999. It looks like it's getting closer and closer to a y value of 2. Let's see if the same thing happens from the other side. So if I look at x values that are bigger than 0, so I'm looking at x values that are bigger than 0, so coming from the right, I'm going to plug in 0.1. So doing that, plugging in 0.1 for x into my function, I get 2.049. If I plug in 0.01, so that's even closer to an x value of 0, I'm getting 2.005. And then plugging in an x value of 0.001, again, that's even closer to an x value of 0. I'm getting a y value of 2.0005. So you can see as your x's are getting closer and closer to 0 from the right, so slightly bigger than 0, but getting closer and closer, my y values look like they're getting closer and closer to 2. So that leads us to believe, or to make the conclusion, that the limit as x approaches 0 of x over the square root of x plus 1 minus 1 is in fact 2. Now, I'm not sure if you maybe thought for the previous example, well, hey, why can't we just plug in an x value of 2? Well, in fact, that does work for this problem, and that is our kind of our analytic approach, if you will. So doing that, you're going to plug in 2 for x, and we're going to simplify. So it ends up being 6 minus 2, which is in fact 4. So those two values do agree. Now what happens if you try to plug in an x value of 0 here into your function? What happens? So I get x over the square root of x plus 1, and then minus 1. That shouldn't have been there, that part of it. Plugging in 0, I end up with 0 over 0 plus 1, and then minus 1. So in the denominator, I get 0. So I get 0 over 0. That's called an indeterminate form. We can't evaluate it that way. So because we can't evaluate it with direct substitution, that's why we have to have other methods and why we're relying on the table to evaluate the limit for example 3. Okay, so looking at another limit, we have the limit as x approaches 1 of x to the third minus x squared plus x minus 1 all over x minus 1. So we're going to look at this using a table again. So go ahead, pause the video, try evaluating this limit, see if you can figure out what the function is going towards. Alright, so here I have my table filled in. As we look at x values getting closer and closer to 1 from the left, we can see that the function appears to be approaching a y value of 2. When we look at x values approaching 1 from the right, so x values that are a little bit bigger, we can see that my y values of my function are getting closer and closer to 2. So the limit of the function as x is approaching 1 is equal to 2. And again, similar to the last example, if you try to do a direct substitution, you try to plug in 1 in for x, you end up with an indeterminate form. You can't have 0 over 0. Alright, now we're going to look at a graphical approach. So the first step is we're going to be graphing our function f of x. So f of x, here we have another piecewise function similar to what we had in our warm-ups. So I'm going to draw my x and y axes.